Let us consider a simple problem to see how backpropagation algorithm works with multi-layer neural networks. Given a neural network, here it consists of two inputs, I1 and I2. Input 1 value is assigned with 0.05, I2 with 0.10. We have an hidden layer here. Hidden layer has got two neurons or two nodes, H1 and H2, and output layer has two nodes, O1 and O2. Now, to this hidden layer nodes, that is neurons H1 and H2, associated with a bias value, that is B1 equals to 0.35. For the output nodes or the output neurons O1 and O2, there is a bias value that is associated, that is B2 equals to 0.60. It is similar, nothing but as I've already told, the computation will be done at the hidden layer as well as the output layer. At the input layer, we are not doing any computation. And each node or each neuron is similar to the working of a single perceptron, where when you consider a single perceptron, okay, it consists of inputs. Even it is associated with the bias value, where the summation is done considering the inputs as well as the weights, and the output of the summation is processed through the activation function, and finally we'll get the output from the neuron. So here whatever H1, H2, H1 and O2, so each node performs the operation of a single perceptron. Hence, each node is associated with the bias value. For the hidden layer H1 and H2, it is B1 equals to 0.35, and O1 and O2, the bias value is 0.60. So when we looked into the backpropagation algorithm, we saw that first the forward pass is done. Then after the forward pass, we'll calculate the error or the loss at the hidden layer as well as the output layer, and finally perform what? The backward pass. So this is what the backpropagation algorithm does. So here, once again, when there is a connection between the input to the hidden layer, the weight is associated here. So weight W1 between what? I1 and H1. So usually the notation, or it is denoted as H1 is 1 and here it is 1. So the weight that is associated is what? J to I, that is W11 equals to 0.15. From year to year, it is 1 to the weight is what? 0.20. Again, the weight from year to year, it is actually denoted as what? That is W2. W2 of that is 1, that is from the hidden node 2 to 1. So this is how actually the representation of the notation is used in the backpropagation algorithm. So wherever there is a link between the nodes or the neurons, the weight is associated. For this one, that is H1, the input will be given from which one now? That is from I1. So this is how the processing will be done, and we'll see how actually the backpropagation algorithm is used to learn the weights of the neural network. Now we'll consider these are the weights. So we have W1, W2, W3, W4, W5, W6, W7, and W8 are the weights, two bias values, and the input is 0.05, etc. And the output that is obtained from the O1 is what we need to calculate. Initial value, the target value is given as what? 0.01. The target value from O2 is given as what? 0.99. So we'll keep this in mind and we'll perform the operation. The first thing we're supposed to do is we need to calculate what? The value at this node. So how we'll perform the operation, that is at this node. From this node we need some output. So this is what? This is a single perceptron. We are going to consider this as a single perceptron. So net H1, it is at the network, at the node hidden layer H1. What we'll do, we'll consider W1 into I1, that is 0.05 into W1, and W2 into I2. So this node W2 into I2 is 0.10 plus the bias value. Bias value is what? B1 into, always X naught value is 1. So substitute these values, we will get 0.3775. And once after we do the summation, it is processed to the activation function. Here we are using a non-linear activation function that is called as the sigmoid activation function, which is a differential threshold unit. So the sigmoid activation function formula is given as what? okay, equals to 1 divided by 1 plus e to the power of minus z. So whatever the value we are getting here, okay, output of this node, that is h1, will be 1 divided by 1 plus e to the power of minus net h1, which is equal to, substitute the value, you'll get 0.59326,992. It is nothing but, consider the node h1. So this node h1 has been associated with the input I1 as well as the input I2. I1 value is 0.05, I2 value is 0.10. The weight for this input W1 is 0.15. The weight for this is, it is 0.20. So this is where the summation we are doing here. So whatever the value that we are going to get from the summation, that is 0.3775. The bias value is also considered, that is B1 equals to 0.35. The output from this is what? It is 0.3775. It is given through the activation function. The function we are using is the sigmoid activation function. From this, the output what we are getting is what? It is 0.59326,992 is what? The output that is obtained from the neuron, that is H1. So whatever the operation we are forming, the complete thing, this is what the operation that is performed at the neuron, that is H1. In a similar way, do the computation at the neuron or the node H2. So net H2 equals to, so we have W3, that is 0.25 into I1 is 0.05, then 0.30 into 0.10 plus the bias value 0.35, you will get 0.3925. This is closest to the nonlinear activation function, that is sigmoid function. 1 divided by 1 plus e to the power of minus net H2, which is equal to, this is the answer you are going to get. So we got the computation is performed at these two nodes. We got the output. One is 0.5932. So this is taken as an input to this node. This is taken as an input to which one? That is this node. So that is how the computation is done at the hidden layer. Now with this, we'll consider this output node or the neuron. So net O1, which is equal to W5 into the output that is obtained from H1. Out H1 is what? 0.5932699, which is calculated previously. So this is taken as an input, then that is X value, that is input value, into weight, then again plus of 0.5 into, again this is the same answer, that is X2 is 0.5988438 plus of the bias value is 0.60. Substituted, we'll get 1.105905967. Then process this through the activation function, sigmoid function, you'll get the answer as 0.7136507. In a similar way, calculate the output or do the computation at the node O2, which is similar. The input to this is what? The output that is obtained from this H1 node and H2 node, which is given here. Take this as the inputs to this node, multiply that with the weights, then again add that with the bias, then process that to the activation function, you will get the answer as 0.77292845. Fine. So this is what the output that is obtained from O1 and O2. Now, the previous target value, that is T value, is already given. O1 equals to 0.01, O2 equals to 0.99. So we got the new output O1 and output H2, that is new output 0.75136,507 and 0.77292846. So this is the obtained output. This is already the target output that is present there. Now, the target output already that is given is 0.01, then T2 is 0.99, but the obtained is what? 0.75136,507 and O2 is 0.77292864. Now, when you compare these two, there is a lot of difference between the values, the target value and the obtained value. So there is always what? A lot of difference. There is an error or a loss between the values that is obtained. So what we are supposed to do is, fine, we need to calculate the errors at these two levels and again update the weights, that is at the hidden layer as well as the output layer. So before calculating the errors, what we are supposed to do is we need to use or calculate the error. The error is calculated by using what? The error function, which is given as E equals to summation of 1 divided by 2 T minus O of whole square. First, you calculate the error for at this level. So at this output, that is E of O1 equals to 1 by 2 T naught minus out of O1. T naught is T1 is given 0.01. O1 is also present, which is calculated. So use these values. Substitute these values in this formula, you will get this answer. Then EO2 in a similar way, substitute these values, will get this value. Then since it is a summation here, you take E equals to E of 01 plus E of 02, which is equal to, add it, 0.298371109 is what is the error or the loss that is obtained. Next, what we are supposed to do, we need to update the weights. So we need to calculate its error term at the output layer and the hidden layer. At the output layer, we'll be using this formula to calculate the error term. At the hidden layer, we'll use this formula to calculate the error term. So we first will calculate the error term now. So at the output layer, so we need to calculate the error term. We have two output units. One is O1, second one is O2. So calculate the error term at both the units. Now, how we are going to calculate? Now, error unit is what? That is OK of 1 minus OK is the formula that we are using. Then it is of TK of for the output unit. Now substitute this for the first one, that is O1, that is delta of O1 is what? Out of O1, then 1 minus out of O1, then T of O1 minus out of O1. Where we got this out of O1 already, we have got this value, that is the output of which one? So we got the out of O1 here, we have already calculated here. So in the similar way, so that is what we need to consider out of O1, which is already calculated. So use those values 0.75136,507 of 1 minus 0.75136,507 multiplied by this is 0.01, which is given. This is obtained. First time when we have calculated the out from this unit, this is what the answer we got. So when you evaluate this, you'll get minus of 0.138498561. In the similar way, calculate the error term at this unit, that is the output unit O2. So out O2 is already we got, we have calculated. Then TO2 is what it is present there. Substitute this, we'll get the values. Now using these two values, we need to update the weight. The weights are updated now by using the formula, that is the new weight. So how it is updated, we'll take W of Ji is what the new weight is, considers the old weight plus of delta of W of Ji. Okay, this is the formula considered from the backpropagation algorithm. That is W of Ji is equal to, use the learning rate, then the output error term, then followed by the input X of Gi. So this is the formula we will use to update the weights. So the new weight. So what all the weights we need to update at okay, by using the error term calculated at the output units O1 and O2 are, update the weights W5, W6, W7 and W8. That is why it is called as backpropagation algorithm. It is not so once we have calculated the error term at the output units and the hidden units, we are not going forward and again updating the weights. Instead of that, calculate the error terms, then backpropagate and update the weights. Then calculate the error terms at this layer with the help of what? The error term that is calculated at the output units, then update the weights W1, W2, W3 and W4. So this is what is the backpropagation algorithm all about. So take W5, take the old value of W5. What is the old value of W5 here? It is 0.40. It is nothing but we are updating this weight. This is what? 1 and 1. So it is nothing but W of 1 into 1. W of 1 1, it is nothing but the weight once again 1 1 plus of delta of 1 1. You update what? The new weight. So this is given as what? Use the learning rate, then the output at this one, that is error term at the unit 1. The error term at what? The output unit is calculated here into the input. The input is what? Obtained with the computation of H1. So whatever the output is given from this H1 is what? The input for this unit, that is O1. So what you are supposed to do, W5 equals to W5 plus of learning rate, then use the error term because we are taking this delta of O1 into what is the thing we need to consider? Output from this H1. Out of H1 is what we have calculated initially. So substitute the values. Okay, the weight is updated for which one now? That is for W5. Previously it was 0.40. Now it is reduced to 0.35891648. This is the new weight. In the similar way, calculate or update the weight W6. So once again, use the same values out H2 because W6, when you consider, it is connected to H2 with ON. So take the out of this H2. But the error term we will be using is the same, that is delta of O1. Same here. Whereas we are calculating W7 and W8. Okay, this is from the hidden layer 1, whereas hidden layer unit 1, this is at the hidden layer unit 2 is what you need to consider, but the error term that is calculated at the output layer unit 2 is what we will be using here. So update the weights. So the new weights are updated after calculating what? The error term from the output layer. Now after this, what we'll do, since we are need to back propagate. Now already we have calculated the error term for this, back propagated, updated the weights for these four. Now back propagate, calculate the error term for these two nodes at the hidden layer, then update the weights for W1, W2, W3 and W4. Fine. Now how to calculate the error term at the hidden layer. So the error term at the hidden layer can be calculated by using the formula, that is delta H of output of H, then 1 minus of OH, then summation of what now? K belongs to outputs. So these are the units that belongs to the output layer. Take the value, that is the weight that is associated between these two nodes into delta K. So delta K is what? The error term at this one, node O1 and O2. So this, using this formula, we need to update or find the error term here. So here there is a summation here. It is nothing but we need to apply this for both the output units that is present at the output layer. So here the error term at the hidden layer unit H1 equals to, you need to take the out of H1, so which is already calculated, out of H1 of 1 minus out of H1, the same value. Then we have what you need to consider, WK of H, fine, which is nothing but when you take this one, this is associated with what now? This is connected to this unit as well as this unit. So when you trace back, okay, you need to consider even this weight. Okay, that is, so it is written as 1 of 1. So W11, that is this one. We need to consider this value. Then again in the similar way, then this value into delta of O1. This is already calculated. Error term is calculated at the output layer. Already previously we have calculated plus of, fine. This H1 is also connected to this. So when I take this path here, it is always represented as what? W of 2, 1. So W of 2, 1, which is nothing but 0.50 into delta of O2, the error term at this output unit. So it is already calculated. Substitute the values here. We'll get the error term at the hidden layer as what? Minus 8.771338887 into 10 to the power of minus 3. In a similar way, calculate the error term at which one? The hidden layer node, that is H2. Okay, that is out of H2, which is obtained already, of 1 minus out of H2. Then this is connected to this and this unit of the output layer. So take 1, 2. So 1, 2. What is the 1, 2 value we have here? It is 0.45. 0.45 of minus of what? The error term at this one, which is already calculated. Then plus of 0.30 into, again 0.30 is what? 0 plus 0.45. So this is already done. Now along with that, we need to consider H of H22. So this has to be sorry, this has to be changed to 0.55. So this has to be changed to 0.55 and perform the operation. So once after updating this value, we'll get what this one, the error term for the node, that is H2. Okay, so after identifying the error term for the node H1 and H2, then what you're supposed to do is, and this should be, so this should be 1 8. The error term at this one. So this is connected, and this is connected to this thing. So here the error term is what? This one. Substitute the values, we'll get minus of 9.954237371 into 10 to the power of minus 3. Now, keeping these two values, we need to update the weights W1, W2, W3, and W4 using the same formula. So update the weights W1, W2, W3, and W4 with the help of what? The error term that is calculated at the node H1 and H2. So W1 equals to W1 plus of the learning rate. The learning rate here we have considered as 0.5 of then delta H1. The error term is calculated at this into 10 to the power of minus 3 into I1. I1 value is what? Here it is 0.05. Substitute this, we'll get some value. In a similar way, update the weights W3, W4, and W2 and W1. Now, after updating these weights, fine, all the weights starting from W1 to W8 are updated. Now, keeping these new weights, what we are supposed to do is, again, we need to repeat the process or start with the new iteration. Okay, where again with the new iteration, instead of taking these old weights, fine, we'll take these new updated weights and we'll perform what? The first, the forward pass. After doing the forward pass, we'll calculate the error term, then backward pass. Fine. When you calculate the error term, okay, if there is what the error, then what we'll do, we'll calculate the error term at the output layer, update the weights, then calculate the error term at the hidden layer, update the weights. Once after updating the weights, again we'll start from the next iteration, again with the new updated weights, repeat the same process. So this process is repeated continuously until the error is minimized. The error is minimized is nothing but the output obtained from this network at the node O1 and O2, okay, must be always similar or equal to 0.01 and 0.99, which is the target value. Fine. Now for doing this, okay, now if you want to achieve the output obtained from these two units, which is almost equal to these values, at least around more than 8,000 iterations are required. So iterations are required to achieve this target value that is obtained from these two units. So this is how the neural network is made to learn the weights. So each time when you start with the new iteration, we'll be using the new updated weights and we are going to perform the operation. So this is how the backpropagation algorithm actually works. Now with this, a little modification is done to the weight updation formula that is used in the backpropagation algorithm. The weight update is made on the nth iteration, depend partially on the update that occurred during the n-1 iteration. Definitely, whatever the weight update that is made at the nth iteration, okay, then partially on the update that occurred what? n-1 nth iteration. It depends. So here WJI is what? Update the new weight by using the old weight plus of the learning rate into the error term, and then the input is changed to delta of Wj of n, that is with n layers, which is equal to, use this same term, plus of, you include one more term, that is alpha of delta of Wji of n-1, which is nothing but for doing the calculation, okay, for updating these values, okay, it is nothing but on the nth iteration, depend partially on update that occurred during what? n-1 iteration. So we will be using this term. So here delta of Wj of n, weight update performed during the nth iteration through the main loop of the algorithm. So we have this term and this term. This is the update rule, and this term is called as what? The momentum. Fine. The weight update is made on the nth iteration, depend partially on the update that occurred during the n-1 iteration. So this is what is called as, we have just changed the training rule by adding one more term that is called as momentum. Now suppose learning in arbitrary acyclic networks. Fine. Now suppose the backpropagation algorithm can be generalized to feed-forward networks of arbitrary depth. It is nothing but instead of having one hidden layer and output layer, if we have more than one number of hidden layers like this, then the weight update rule is retained as it is. Um, changes identity procedure by computing what? The delta, the error term. Okay, each time when we are updating the rules, the error term formula keeps changing at each layer. So in general, okay, if I consider we want to calculate the error term at this layer, that is delta R value for a unit R in layer M, if I consider this as layer M, is computed from the delta values at the next deeper layer. Okay, computed from, we use these values, then compute here according to M plus 1, 2. So it can be generalized to, okay, this one, the weight update or the error term at this layer, that is delta R equals to OR of 1 minus of OR, then sigma of S belongs to layer of M plus 1. In the previous one, when we are calculating the error term at the hidden layer, it was a delta of H equals to 0 of H of 1 minus OH, then sigma of K belongs to output units, that is the last layer. So same here, then W of SR, the weights between these things is what we need to consider. This is R, then definitely this is S. So SR into the error term at this layer, that is at the layer S. So this step is repeated for any number of hidden layers in the network. So this is what the learning in arbitrary acyclic networks, when we have more than one hidden layers, this is how the error term is calculated. And it can be generalized and generalize the algorithm to any directed acyclic graph, regardlessly of whether the network units are arranged in the uniform layers. In the case that they are not the rule for calculating, that is the error term for any internal unit, just downstream it, okay, to any number of layers. It is nothing but S belongs to downstream of R. So where downstream of R is the set of units immediately downstream from unit R in the network, that is all units whose inputs include the unit R. So the previous formula is generalized here with this one.